Good afternoon to the examining committee and to our esteemed guests. Today we are going to be presenting our game Kombat Legends. I am Jamila Sadek and my partners are Mohamed Moussa and Aly Hesham. We divided our presentation into 4 pillars. We start by a quick overview of our project objective, the problems it solves, and the edge over competitors' solutions. Then, we move on to the system design and architecture and the implementation of its algorithms. Thirdly, we have an overview of the algorithms chosen to implement the AI and the process of its training. Finally, we will discuss the future developments and the overview of the complications faced in the implementation phase. Our project objective is that we aim to produce a game that will be engaging with the users by having a different type of AI implemented, rather than following the general trend of fighting games. Therefore, in order to fully satisfy our project objective, we had to research the gaming world. Games have been a major factor of a human's life and development ever since the early years of human existence. With human evolution came the game evolution and development. The computer game industry has grown rapidly over the last decade. Currently, computer games is the biggest sector of the entertainment industry and among the wealthiest sectors. This is why we chose our project to be in the gaming world. But before entering this world, we must assess the problems that exist in it, like, for example, maintaining user retention. User retention in any game requires consistent efforts from developers. To effectively engage users, you need to understand their reasons to leave. Users easily get bored with one type of play. Some common reasons include bugs, lack of gamification, complicated interfaces, etc. Another problem is that the market is absolutely flooded with games, and it is very hard to introduce something that is unique. Finally, most games have a relatively simple AI, and that most likely makes it less entertaining to play with. After talking about the problems that the gaming world is facing now, we are going to discuss our proposed solutions and different approaches in designing and developing our game. Firstly, we increase the user retention by making a more challenging AI. Secondly, our attempt to break the flooded market is by developing a 2D retro game targeting nostalgia. And finally, we developed an AI agent using reinforcement learning rather than the normal, simple pathfinding AI implemented in most games. These 3 solutions proposed before structured our roadmap while getting into the architecture and design of our system. As we dove deeper into designing our system, the architecture evolved continuously until reaching our final system architecture, as you can see on the screen now. The components of the architecture are divided under 2 main umbrellas. The first is handling the gaming environment, and the second is focusing on the AI component of the system. The system design of the game is a one-step further analysis of the system architecture that encompasses all the components of it. As previously mentioned, the game that is developed is a fighting game. Fighting games are basically built on typical multiple tiers of mechanics, starting with a wide variety of different movements, special attacks introduced within the game. And that's why the system design needs to be focused on that. The graphical user interface, the AI agent specifications, the game environment, all represents important components of the system design. The class diagram shown in the appendix at the end of the presentation covers all the other components of the data description.
So now I'll be introducing the AI we implemented in the game and the process we carried out. As we mentioned before, we needed to have all the game physics per our prototype ready to be able to implement any kind of AI. So after finishing the final touches of the game physics, we started integrating the pathfinding AI for our machine learning agent to have a ready environment to train in. And after the environment being ready for the AI to train in, the agent was actually integrated successfully. We initially planned on using Q-learning or deep Q-learning in our case, using a neural network for this model, but we have faced some complications, as Unity didn't actually support the integration of Q-learning for our model. In our case, Q-learning was very complex and the training was very slow, so we had to resort to a different type of reinforcement learning, which is policy gradient methods. Reinforcement algorithms tend to fall into two distinct categories: value-based and policy-based. Q-learning and its deep neural network implementation are examples of the former. Policy gradient methods, especially in our case proximal policy optimization, as one might guess, are examples of the latter. While value-based methods have shown performance that meets or exceeds human level, in a variety of environments they suffer from some significant drawbacks that limit their variability across the broader array of possible environments. Further limitations of value-based methods lies in the topology of the parameter space. For example, the action value can be quite complex and has many local minima that can trap the gradient descent algorithm and can limit the algorithm's rewards optimization. But policy-based methods do not suffer from such drawbacks, as they are attempting to approximate the agent's policy rather than the action value function. And in our case, PPO strikes a balance between this ease of implementation and sample complexity and ease of tuning. It trains in an on-policy way, unlike Q-learning, so it doesn't store in a replay buffer in an experience. So it only trains over the course of the training. The policy typically becomes progressively less random as the update rule encourages it to exploit rewards that it has already found. And policy gradient methods learns directly from the environment. And once it learns enough to do an update, the experience is then discarded. So it does not store the experience in a replay buffer as Q-learning did, which reduces the complexity and removes the limit that we had while we were using Unity. And in traditional policy gradient methods, the agent samples rewards from the environment and uses these to compute the discounted future rewards at the end of each episode. These rewards are used to weight the gradient descent such that the agent assigns a higher probability to the actions that lead to higher future returns and less probability to those actions that lead to lower future returns. And in this equation, you can see how the policy gradient loss is calculated. The log pi theta is the neural network that takes the observed state as an input and suggests action to take as an output. So this is just the log of the probabilities. And the hat A is just the estimation of the relative values of the selected action. And this is calculated by setting our gamma value while setting our PPO. So this determines how our agent will act, which is in interest of our more futuristic rewards or nearer futuristic rewards. So in conclusion, PPO helped us a lot in adapting with Unity's requirements and still having a functioning agent for our environment.
Hello, now we're going to talk about the training process that we made, the training process for our machine learning AI to reach the state it turned now. The training process was split into two. The first one Ali will talk about later, which was the training of the two agents that we made against each other to make them improve. The first method we applied in order to see the outcome of it was training our pathfinding AI that we demonstrated in the previous presentation with the machine learning AI that we have done. And at first, of course, the pathfinding AI won every round easily because the machine learning AI did not know what to do. He had rewards, which means he had a reward with a positive reward if he won. He had a positive reward if he hit the other AI. He had a reward if he won the whole round, and he had a negative reward if he got hit and if he kept spamming the hit button in the air, or he had a big negative reward if he died, if he lost the round. Now, as you can see from the graph, at first the pathfinding AI kept winning, but gradually our machine learning AI have improved until it reached a point where it can beat the pathfinding AI about 90% of the time, or even more than that, maybe 95% of the time. We're going to see in a video later, we recorded 3 times, and from the 3 times, the machine learning AI that we have made have beaten the pathfinding AI.
So after training the agent against the pathfinding AI and viewing the results that Mohamed showed us, we decided to train the agent against a pre-trained model. So now we have the neural network and the weights stored. So we decided to have this model assigned to one of our characters and then have the other character train using the same algorithm. And you will see the results of this agent in the demo. So at the end, we would have two agents. One trained against the pathfinding AI and one trained against a machine learning one.
Next, we have to talk about some challenges. Okay, now we have our demos. We are going to show you two videos. The first video shows a fight or a round between, or multiple rounds, sorry, between our pathfinding AI and our machine learning AI. The machine learning AI or is in the blue character, the Mega Man character on the left, and the pathfinding AI is on the Mario character on the right. This is for the first video. As you're gonna see, Mega Man beats him the 3 rounds that we have recorded, as you're gonna see in the video. The second video has two machine learning agents playing against each other. In the two agents, we have Mega Man as the agent that trained against the other agent, and Mario is the agent that trained against the pathfinding AI. As we're going to see, the agent that trains against another agent of the same machine learning AI has better results. He always wins, even against an agent of the same PPO machine learning AI. So when we train when both the AIs that trained had the AI of the machine learning one, the training procedure was better and the results were much better, as we're going to see in both of the videos you're going to see. Okay, now before we see both of the videos, I just wanted to highlight something. The first video we have is from the pathfinding AI versus learning AI. As you can see, this would be a very easy win for our PPO AI or our machine learning AI. As you can see from both of the health bars of the characters up, you can see it will be an easy match for our machine learning AI. He will only take about 2 to 3 hits before winning. However, the second video, which shows that the training process is better when we put two machine learning agents training against each other, because in the second video, when we have two agents playing against each other, we will find the result is really close. Sometimes, every time, despite our having one superior AI, done more training on the other AI, the result is really close. You will find each time their health is about the same when someone wins. Both characters are one hit away from losing the round. So that's something I wanted to highlight. Look at the health bars, you will notice the difference between the training between the two AIs. Thank you. Okay, now as you see, the pathfinding, the two trained machine learning AIs, the result between them was really close. At sometimes you could see that the health between them, the difference was only one hit. despite having our superior AI that trained with the other, but however, the result was really close between both of them. One moment, sorry. Next, we have to talk about some challenges we faced during our implementation. The first challenge of all that we were not able to implement the Q-learning AI that we mentioned before, because the Q-learning AI was not really supported by Unity and would have been really difficult and really time consuming to do it. Not to mention that PPO is basically the same, it's even better in some stuff, like Ali said. And it's basically the same. It's also on reinforcement learning, and it is supported by Unity. So it makes our job better because setting up the environment and stuff like that is easier. Our problems were two kind of problems, like technical problems because we were working in AnyDisk, and actual problems in the coding and stuff like this. Let's talk about the technical problem first. Due to working on AnyDisk, our input and viewing of the screen was very weak. So we had an input delay from the mouse or from the keyboard about 2 to 3 seconds, which made it extremely difficult to play as a character against the AI, and made it sometimes extremely difficult, sometimes even to turn on the game or to see what's happening during the game, because we need to see what's happening in order to get feedback, in order to improve the training and so on. So that part was extremely difficult because sometimes of the day the internet was so slow, the input delay was big, so we couldn't work, so we had to wait until the internet became better and so on. Second thing, we had problems with the coding itself. After setting up the AI, we had to, every AI run is called an episode, where the AI has to start an episode and end it in order to take all the information and store it. We had to know when to begin the episode and when to end it. We begin the episode when the game starts, of course, and the episode ends every time our AI dies. So he knows the episode has ended and he takes all the rewards, positive or negative, he has took. The second thing we had to fix, or the second thing we had to do, was know when to add the rewards. Yeah, adding too much positive rewards or too much negative rewards, too much rewards in general, it's maybe not good. Or adding rewards of big numbers, like adding 50 or even 15 reward when the player wins, will ensure he always has a positive reward and he will not learn. So we had to normalize our values for the learning and for the rewards. So they're all about the same size, between 0.25 and 1. So when he wins, we give him a reward of positive 1. When he loses, we get a reward of negative 0.75, for example. And say when he gets hit, he gets a negative reward of 0.1, just to not increase the. When he spams, when he keeps hitting all the time, he gets a little negative reward to enforce him not to do that. And after knowing what to do and when to add the rewards and stuff, we have reached the result that you will see in the videos later, and I think it's a very good result. Next, we have some future enhancement that we're going to do after our thesis to improve the game, to actually release it commercially when we were planning to release it. The future, we plan to optimize the AI agent more so he looks more like a human player. Right now, he looks really like you can really see that his actions are a little bit looks like an AI. We need to optimize the reward because it can be optimized more. It can be optimized to even not be beatable like we said in the first, but we didn't have much time to implement that phase. So we can improve this. Other than this, we're going to add, of course, some improvements to the game itself. We're going to add more characters and more levels. We were tight on schedule with adding stuff to the game because the more important thing was the AI and stuff. But now that after finishing thesis, we can work on adding stages and adding multiple characters and a bigger menu and all that stuff. Other than this, we're planning to develop our game to be compatible with most systems like macOS and Linux and iOS. It's not going to be that hard. It's not going to take much time. We just need the memory and all that stuff. And we need the memory and all that stuff, I mean the libraries, in order to make it work on these devices. Okay.
Now that you have seen our demo, let's briefly go through the milestones that concluded our journey of reaching Kombat Legends. Firstly, we created the system design and architecture. Then, we created a complete gaming environment with cross-platform players. We then designed a simple pathfinding AI and fully enhanced the game environment. Finally, we implemented an AI agent using PPO algorithms and trained it with the pathfinding AI. Our capstone outcome is for us to do a commercial product. Our progress towards that outcome has been divided into 4 parts. First, we researched different gaming engines to find the most suitable game engine for our game environment. Then, we finally came to the decision of having Unity as our game engine as it is the most suitable for our system design. Secondly, we had to have a complete 2D platform environment for our game in order for the AI agents to be able to train on. Then we developed and trained AI agents to fully achieve our project objective. Finally, our product will be an online downloadable game for the market. Now, Kombat Legends is ready to be commercialized, and our plans towards the revenue streams and cost structures have been addressed by the business model shown in the appendix at the end of the presentation. Thank you, and now we welcome your kind feedback.